Okay, so let me remind you what we were doing last time. So last time we were proving fundamental theorem of curves. What was the theorem? So let beta 1 and beta 2 be two arc length parameterized regular speed curve, regular space curves in R3. Well, we already said that having the same curvature kappa S and torsion tau S functions. And there is a rigid motion. Rigid motion. Let's say F diyeyim. Ne yazmıştım geçen sefer? F mi yazmıştım? Phi mı? F, okay. Of R3 so that F of gamma 1s is equal to beta 2s. And I will show once we prove the theorem that a rigid motion can be written in two ways. Composition of a translation and then an orthogonal transformation, or vice versa. First an orthogonal transformation, then translation. They are both equivalent things. So far, I guess we first did translation and then orthogonal transformation. But in the proof, I'll do the other way around because, you know, I just wrote it that way. You can write the proof the other way around, but let me just stick to my notes. So what was the proof? We pick any S0 in the interval I and consider the Frene frames T1S1, T1S, N1S, B1S, and T2S, N2S, and B2S of beta 1S and beta 2S. Okay. But let me choose this frames at the point S0, at this at a specific point. Okay, at this point that we picked. So let's say we have something like this. This is my interval I. This is my interval I. And here I had point S0. And here we have beta 1. and this is the point beta 1 S0. This is the point, okay, beta 2 S0. And I have the frames. Okay, let me use sarıları bitirmişler. Okay. Biz de mor kullanırız. Okay. So T1 S0 and 1 S0, and the cross product of these two is something like this, B1 S0. All right, and here we have T2 S0 and 2 S0, and the cross product B2 S0. Okay. Now, what we do, first, choose a translation, T from R3 to R3 with T of beta 1 of S0 is beta 2 of S0. So what is this T? T is just the, indeed, T is just the translation along the vector, let's say A, which is beta 2 S0 minus beta 1 S0. So it is just the translation along this vector, okay? Joining this point to this point. So T of V is just V plus A, okay? All right. Now, then, since both these frames, both the frames, okay, T1 S0 and 1 S0, B1 S0, and T2 S0, and 2 S0, and B2 S0 are positively oriented. These are, both of them are orthonormal bases, right? Orthonormal bases for R3. Moreover, they are positively oriented, meaning that the cross product of the first two vectors is the third one for both of them. So I have a unique orthogonal transformation which sends this basis to this basis because they are both orthonormal. And moreover, that matrix which sends this basis to this basis has positive determinant because they are both positively oriented. There is a unique orthonormal unique, okay, orthogonal, transformation, C from R3 to R3, so that uh, this T1 S0 is T2 S0, C N1 S0 is N2 S0, and C of okay, B1 S0, B2 S0. Moreover, C has positive determinant. Okay, because both of them are positively oriented. Now, let F to be first we rotate, translate and then rotate. Okay. Sorry? Yeah, I did so, but it doesn't matter. Since I did this setup, first I moved the point and then rotated. I'll do it this way, but then I'll show that, it doesn't really matter, okay? So what we do is the following. I first carry this point to this point via a translation, okay? So this curve comes here like this when you translate along this vector. And then at this point, I rotate them, okay? Then F of beta 1 of S0 is what? F of beta 1 S0 is just okay. Bir dakika. Yok, evet ya şey yapmak lazım galiba. Yani çünkü bunu buraya taşıdıktan sonra döndürdüğümde bu nokta sabit kalmayabilir. Okay. I'll do it the other way around. Okay. Let me do it this other way around. Okay. First choose an orthogonal transformation G.
Hocam tahta kaldı.
Okay, sorry. First choose an orthogonal transformation so that C of T1 S0 is T2 S0. C of N1 S0 is N2 S0. And C of B1 S0 is B2 S0. So what you do, before you translate this curve to this curve, you first rotate it, okay? So let me draw a picture here to explain what's going on. So here we had beta 1, and here we had beta 2. First, I rotate this so that the frame of both of them are the same. So when I rotate this, I will get something like this. So this is C of beta 1. The thing is that at this point, they have the same frames. So both tangent vectors are the same. Normal vectors are the same. And so T, C of T1, C of N1, and C of B1. And here this is ters yaptım. Şu T burası olacak. Okay. This is C of T1, C of N1, okay, B of N1, no, T, okay, B1, and this is N2, T2, and B2. At the point, so what is this point? This point is, this one was beta 1 of S0. This is beta 2 of S0. What about this point? This point is C of beta 1 of S0, right? This point after the rotation. But the frames are now the same, okay? Are the same. And then we do what? Now choose, let T be the translation along the vector. Which vector? Beta 2 S0 minus C of beta 1 of S0, okay? Let F be the composition, so which is just T composition C. Then what is F of beta 1 of S0? Well, this is just T of C of beta 1 of S0. But T of beta 1 of S0 is what? T is the translation along this vector. So this is just this gadget plus the amount of translation, which is just beta 2 of S0 minus C of beta 1 of S0. And these are canceled. Therefore, I have beta 2 of S0. So that translation just sends this curve to here, so that this point moves to this point. Şeyden emin değilim tabii. Of course, I am not sure at the moment. You know, this point, beta, where was it? So F sends this point first to this point via C and then via translation to this point. So this curve, let's say this is a green curve, is moved to a curve here. It passes through this point, but at the moment, it may not be the same curve, right? Maybe it is something different than beta 2. The only thing we know that it passes through this point. But we will show that actually that cannot happen. They are the same curve. So this white curve and the green curve are the same. How can we show that? Okay. Now, so both f of beta 1 s and şunu da söyleyeyim before I say so. Well, we know that rigid motions doesn't change the curvature and the torsion, right? We know that F, which is a orientation preserving, positively oriented. Ne diyorduk ona? Orientation preserving mi diyordum? Okay. Preserving. Isometry. Preserves both the curvature and torsion functions. Beta 1 and beta 2 had the same torsion and curvature functions. I moved beta 1 via F. Beta 1 has changed, but its torsion and curvature functions didn't change, okay? Because F preserves those functions. In particular, F of beta 1 S has the same curvature and torsion functions, kappa S and tau S as beta 1 S and beta 2 S. Değil mi? The curvature and torsion functions of F of beta 1 are the same functions, kappa S and tau S, which are the curvature and torsion functions of beta 1S and beta 2S. So what we have is then the following. F of beta 1S and beta 2S both passes the point through the point beta 1S, which is beta 2S, and they have the same curvature and torsion functions. Okay, so let me draw you a picture. I have, okay, so şey yapayım. Tahtayı da değiştirelim. Okay. So this is f of beta 1s, and this is beta 2s, and they passes through this point. And what we know is that they have the same frame at this point. Onu söylemedim, değil mi? Torsion functions. Also, they have the same frame at the common point. So if you draw the tangent, normal and binormal vectors, they are the same. Of course, in this picture, they don't, they don't like, I mean, they don't look like they are the same, but so because the picture is wrong. Yani isterseniz bunu nasıl çizerseniz ki, değil mi? Hem aynı olsunlar hem aynı olmasınlar. Okay. Yani I don't know. T and B. They have the same frame at this point. Okay. Well, then we have what? Hence, beta 2s and f of beta 1s are two solutions of the initial value problem. Which initial value problem? This one. T and B prime 0 kappa 0 minus kappa 0 tau 0 minus tau 0, and here I have T and B. Well, actually, I should say not beta 2 and f of beta 1, but I should be careful. The triple. Şöyle yazayım. Okay. Solution olan şu. Hence, the vectors T2S, N2S and B2S. Bunu da şöyle yazayım. Bu kötü bir yazım. Şöyle yazalım da. T2S, B2S, no, N2S, B2S, transpose, and differential of this. What was the differential of F? F was T composition C. Its differential is just this. Differential of translation is just identity. Differential of C, this is a linear map. Its differential is the same as itself, so it is just C. So this is okay. Nasıl yazayım onu? C of T1S, C of N1S, C of B1S, vector valued functions, of course, as functions are both solutions of the initial value problem. Which problem? This problem, right? They both satisfy this equation because they have the same curvature and torsion. Therefore, they both satisfy this equation, and they both satisfy the initial condition that of course, transpose of this initial condition that T and B at the point S0 is just beta. Okay, so T2 S0, N2 S0, and B2 S0. Okay, they satisfy this differential equation together with this initial value. So here, what's happening? I have this point, okay, beta 2 of S0. From this point, there passes two curves, okay, there passes two curves like this, and both of them are solutions of this differential equation, I mean T and B, and they have the same frame at this point. But, you know, these are continuous functions, and such a system has a unique solution. Therefore, if two solutions agree at a point, then they agree at all the points, not just at this point, but at all the points. So now, by the uniqueness of the solution of an initial value problem, the frames which frames, so T2S, N2S, B2S, and C of T1S, C of N1S, and C of B1S agrees at all points. Değil mi? Bir noktada eşitlerdi birbirlerine. Ama değil mi? They are the same at one point, but they satisfy the same differential equation, first order equation. Therefore, they must agree at all points. So the conclusion is that okay.
Hocam, bir de tahta şu an zoom yapmış durumda da onu düzeltebilir misiniz?
Tamam. Kendi kendine zoom yapıyor. Okey. Şimdi iyi değil mi?
Evet hocam, iyi.
Tamam. Siz bana eğer şey olursa söyleyin, çünkü ilk ayarladığımda düzgün oluyor. Sonradan bir şekilde alet kendini şey yapıyor. E, Bir şekilde değiştiriyor konumunu. Okay. So these two vectors are the same at all points. In particular, T2S is equal to C T1S, okay, for all S. Well, what is T2? T2 is just so derivative of beta 2, right? And this is C of T of beta 1. Yeah, I don't have this, just T. C times T1. T1 is just beta 1 prime S. This is true for all S. Therefore, and they are the same. Okay, so beta, this means beta 2S is just C times beta 1 S plus a constant vector, okay? But yeah, so okay, I don't have this. I just integrate this, right? This is a vector valued function. This function and this function are the same. There is the C here. So when you integrate this, you will get this one for some vector V, right? Integration constant. But then we know what? We know that beta 2 of S0, C of beta 1 of S0 plus V, and V is just beta 2 of S0 minus C of beta 1 of S0. And that has a name actually, right? It is this term here, beta 2 S0 minus C of beta 1 S0. So this is our vector V. Okay, this is the vector V. So this means what? This means okay. Hence, beta 2 of S, which is just C of beta 1 of S plus V. V is the vector beta 2 of S0 minus C of beta 1 of S0. But this thing is just T of C of beta 1S, right? Because T is just translation along this vector. And this means T composition C, this is just f of beta 1 of s for all s. Okay, so beta 2 is just the image of beta 1 under the orientation preserving isometry f. Tamam mı? Okay. Sorusu olan var mı? So most of the job actually is done by the theory of ordinary differential equations, right? We just use existence uniqueness theorem of the solutions of initial value problems, systems of initial value problems. Okay. Şöyle bakayım örnek. Kitabı da almayı unutmuşum yanıma. Orada vardır örnek herhalde ama. Okay. Yeah. Yeah, for each kappa and tau functions, you can write down this system and its solutions are just curves. Yeah. So a space curve is basically determined by two functions, curvature and torsion, right? Once you know the torsion and curvature, you know the curve. You just need one point of the curve and the frame at that point, right? If these are known, suppose these two functions are given to you, and you know that your curve passes through a point like this, and I tell you what are the tangent, normal, and binormal vectors at this point. I say that this is the tangent vector. Okay, this is the normal vector, and this is the binormal vector at this point. Okay, then I know that there is a unique curve, okay, through this point, so that the frame at this point are these three vectors, having this as the curvature function and this one as the torsion function. So I have a curve like this, okay? This curve is uniquely determined. That's the content of the theorem. Tamam mı? What is nice about this, you know, in general, to specify a space curve, you need three functions, right? Coordinate functions, x coordinate, y coordinate, and z coordinate, right? Beta s. It has three functions, right? X of s, y of s, and z of s. But this theorem tells us that actually you don't have this freedom of three functions. Actually, they are determined by two functions. Okay. Yeah, it's kind of interesting. Okay, now let us give a break. After the break, I'll start a new chapter. Well, to specify a curve, you write three functions, right? For both x, y, z coordinates. But this theory tells you that actually a space curve is determined by just two functions, curvature and torsion. Okay? Yeah.